In the last class, we introduced hidden Markov models, a graphical model in Bayesian machine learning. And we talked about one kind of inference, which is filtering. And in this class, we'll extend our conversations about inference and hidden Markov models. So we'll first look at the basic concepts of hidden Markov models and review what we talked about last time. Then we'll look at three new inferencing techniques known as smoothing, prediction, and decoding. So let's recall that hidden Markov models are a graphical model. They consist of a bipartite graph in the sense that there's one set of nodes or units that are called hidden units, and we'll denote those H1 through capital T, where T is the current time. And they generate the observations that we see, and the observations that we see are designated V1 through Vt for the visible units. And these are the actual values of variables that we observe in our environment. Now, the V of t could be continuous, but for the example we did last time and the example we'll do this time, we'll consider them to be discrete. As we saw in Bayesian networks generally, this directed graphical model, this Bayesian network, allows us to provide the joint probability distribution for all the nodes in the network. And this means all the hidden units and all the visible units. And that can be just expressed as just the product of conditional probabilities. And these conditional probabilities, since we have these Markov properties, they're only going to be dependent upon the previous state and not any past states beyond that. So for example, the hidden units are connected to each other, but their values, the probabilities of them, only depend upon the previous state and not on any other value, not on any other state. So the common inference problems in hidden Markov models are known as filtering, prediction, smoothing, and decoding. And last time we talked about filtering, which is basically inferring the present state by looking at all the values that we've observed in the visible variables from the beginning all the way up to the current state. In prediction, we infer the future. So it sounds similar to filtering, but the difference here is that we're now predicting a hidden state in the future instead of the current hidden state. We want to know a hidden state in the future. So that's the difference. But again, it's conditional on all the visible variable values from the beginning up until time t. And in smoothing, we infer the past. We want to know what hidden state we were in previously. So whereas for filtering, we want to know what the hidden state is where we are now at the current time. In smoothing, we want to know where we were at some time in the past. Which of all possible states were we in some time in the past? And again, we're going to use all the information that we have from the visible variables from the beginning up until the present. Decoding answers a similar question as smoothing, but instead of asking just one point in the past, it's asking for all points. So it's saying, what is the most likely path that we took along those hidden states in order to get to where we are now? So of all the possible paths that we could have followed, which one is the most likely in order to get to our current state? So let's first look at smoothing. In smoothing, as we said, we're going to find some point, hidden point, but it's going to be some point in the past. So we're going to look at some time point in the past and ask the question, what was the hidden state at that time point in the past? So it will update what we might have learned about where we were. For instance, if we've obtained it up until that time point using filtering, well, now we've gone on and we can go back and say, okay, where now do we think we really were at that time point? One way to compute the smooth quantity is to consider how this the set of hidden nodes partitions the series into both past and future. And we can see that when we look at the joint probability of the hidden state at time t, and all the visible states from the beginning all the way up until the present. So at some hidden state, time t, which is in the past, the question is, What do we know about where that is given all we've observed from the beginning until the current state? And we can divide that visible state sequence up into two parts. We can divide it up into the part that is all the visible states up until the time point where we want to know what the hidden state is, and we've designated that here as small t, as well as all the visible states that we've observed from that time, and we'll say t plus 1, the next time period over, up until the present. So we can separate it that way. And that way of seeing things then allows us to see things as past and future. Because when we look at the probability of the hidden state at t and then v of 1 to t, that looks exactly like our filtering problem. And it should. That was our filtering problem. If we were actually at that time point, as opposed to being at some time point in the future from it, then that would be the filtering problem. But now it's the past. It's a version of the filtering problem, but it's just in the past. Whereas p of v of t plus 1, so the next time period over from that point in the past we're interested in, all the way up until the present, that represents the future. It represents everything that's happened since that hidden state. And that's conditioned on the current hidden state, the hidden state that's current at that time, h of t. And it's also conditioned on all the points that occurred from the beginning up until t. But notice, because of that, if we know what the hidden state is at time t, then the states, the visible states from t plus 1 to the present, to capital T, are independent of all those past states. So we can remove that. And now we're going to write this as just alpha h of t, beta h of t. And we can see alpha h of t in this context is what we call the past, and beta h of t is what we call the future. That's going to be p v of t plus 1 to capital T given h of t. All right, we now have what we need in order to do smoothing. And in fact, we can do it in a parallel way, so we call it parallel smoothing. And we're going to compute both sides of this smoothing operation using forward and backward operations or recursions. In the forward one, it's essentially the filtering operation that we performed before. It is the filtering operation we performed before. So we're going to find alpha h of t from the forward alpha recursion that we saw in filtering. Now the backward state, we're going to compute that term beta h of t using a backward recursion. And we'll describe that backward recursion in the next slide. These forward and backward recursions are, interestingly enough, independent of each other, and therefore you can actually run them in parallel. So if you wanted to process them fast, you can run them in parallel and do it much quicker than you could if you did them sequentially. This forward and backward operation is in fact called forward-backward. So we have a forward recursion, a backward recursion, and when we put them together, we call it the forward-backward recursion or the forward-backward algorithm. So let's take a look at the backward recursion. We already know about the alpha or forward recursion, so let's look at the backward recursion. And in the backward recursion, we're computing this conditional probability of the visible states, so the states from t to the current state. So this is the future in terms of the state that we're interested in, which is at time t, the future. So it's all the states going forward in time from that point, given the hidden state that we were in previously to the one that we want to find. So at h of t minus 1. And not surprisingly, from what we've seen over and over in the course, we're going to find this using conditioning. Only in this case, notice that we're conditioning on h of t, because we've given the conditioning in the conditional probability on the left side of the equation is h of t minus 1. So now we're conditioning on h of t. This is our backward recursion then. We're looking at h of t and we're saying, all right, what are all the possible values for h of t given the value of h of t minus 1? As we saw before, we get a lot of cancellation when we write this out in terms of the conditional probabilities. And in fact, we can see that if we look at the conditional of the visible state at time t, it's going to be independent of all the visible states from t plus 1 to t, and it's also going to be independent of h of t minus 1. It's only going to depend on h of t because that's the way this HMM works. It's not dependent on the past hidden states. It's only dependent on the hidden state for the visible variable that we have. So v of t is only dependent, given h of t, it's only dependent on h of t and not of anything in the past or anything in the future for that matter. It's not dependent on h of t minus 1 in this case. The next conditional is just straightforward. It's the conditional probabilities of observing the visible variables from the current state, t plus 1, not the current state, from t plus 1 all the way up until the current state, capital T. And that and the h of t, then, the thing that we're conditioning on in this conditioning argument, given the h of t minus 1, which is the ultimate conditioning that we have on the left side of the equation. So we're removing, by our conditioning argument, we're removing all of these h of t's by conditioning over all the possible states that you can be in at h of t, and that's where the sum is. Okay, so now the next thing we do is we take that last term, that v of t plus 1 to capital T, and h of t given h of t minus 1, and we break it out. We break it out again using a conditioning argument, and this conditioning argument says we can look at the conditioning on h of t minus 1, and when we put the conditioning of h of t minus 1 into it, then we get the v of t plus 1 to t to the present time given h of t and h of t minus 1. Well, again, it only depends, all those states only depend on the current, on the h of t and not at the h of t minus 1, not on this past state, the past value that we were in, hidden state we were in at t minus 1. So that cancels. And that is times the probability of being in hidden state at time t given hidden state at time t minus 1. Okay, so this then defines this this beta recursion, and we can set beta, and we'll call it beta h of t, equal to this conditional probability, the probability of the visible states from t plus 1 to the present, to capital T, given h of t, and that'll be beta. And then we can define a beta recursion that just looks at where the beta is at h of t minus 1, and we're summing over this all possible values for h of t. So notice that we're at a state in the future from h of t minus 1 now. Again, we saw that above. We're conditioning on a future state from it, and we're saying, okay, we've got that conditioning. We're going to look at the probability of the visible state at time t, the hidden state at time t, the transition from the hidden state at time t minus 1 to the hidden state at time t, and then this beta expression, which is the conditional of the visible states from t plus 1 to the current given where we are, the hidden state at t. And you can see we're going backwards. We're going backward from the future state at h of t, the future hidden state at h of t, to the past hidden state at h of t minus 1. So unlike the alpha recursion, we're going backward in the hidden Markov model rather than going forward in the hidden Markov model. And whereas in the alpha, we had to start with an initial condition on where the hidden Markov model starts, in this case, we're starting on a condition for where the hidden Markov model is ended. And we say that the beta for h of t is 1. That's our initiation state for this beta recursion. So with this, we can now compute the interesting thing the thing that we're interested in finding, which is the smooth posterior. Remember, our smoothing is interested in finding what the likely state is for time t, some time little t in the past, given all that we've seen from the beginning all the way up until the present, okay, all the visible states, we want to know what that is. And so we're going to find that conditional probability then, and it's just going to be the product of the alphas and the alpha at h of t and the beta at h of t divided by the normalizing value, which is just summing the product of those alphas and betas over all possible values for h of t. And that'll give us that probability, and hence we can compute, for instance, the most likely one to be in at time t, little t. So to get an idea of how smoothing works, let's look at the example we had from the last class. And recall that example, we had Sally's apartment had a burglar in it. Her burglar alarms had gone off, and the question was, where was the burglar? And in the case of last class, we were looking at filtering to answer the question of where the burglar was after 3 hours. So Sally had seen the burglar alarm go off in rooms 1, 3, and 3, respectively in hours 1, 2, and 3. And the question is, where was the burglar at time 3? Well, now we're asking in the smoothing question, we're at time 3, in hour 3, and where's the burglar at hour 2? And we get that using these alpha-beta recursions. And the answers are shown here for computing those alpha-beta recursions. So go through the little recursive equations we've given and satisfy yourself that you can come up with these answers. And notice that the answer to the particular question we have, where is the burglar at hour 2, is given by the probability of the hidden state at hour 2, given the visible states from 1 through 3. And you can see that the most likely room that the burglar is in room 3 with a probability of 0.7. All right, the next inference problem that we have in hidden Markov models is prediction. And in prediction, we actually are looking at what's going to happen at some future state beyond where we currently are. So we're currently at time capital T. We're going to use everything we've learned up until capital T in order to predict where we may be at some future state. So this will form the starting point for our computations. And then we can look at some points in the future, like 1 or 2 or k steps in the future from where we are now. If we look at predicting 1 step out, we can easily write that. So here's the probability of the hidden state at time t plus 1, given what we've observed from now, or from the past, from the beginning, up until the current state. We're at time t. And the way that we find this, again, is we're going to condition, and we're going to condition on the value of the current state, the hidden state. But oh, by the way, we know what the probability is that we can use in that conditioning equation because we've determined it through filtering. So we can easily write then the equation as the probability of h of t plus 1 given h of t. And where do we get that from? We get that from our transition matrix, the transition matrix between hidden states. And we get the probability of h of t given the visible states from 1 until t from the solution to our filtering problem. So we can easily answer this prediction question. And predicting a future observation is similarly something that we can easily answer. So for instance, a 1 step ahead prediction is given by the probability of v of t plus 1 given v of 1 all the way up until the present, up to t. So this is our prediction. We want to know what the next visible state will be given what we've seen up until now. Well, now we're going to condition on both h of t and h of t plus 1. And again, we can easily find these. Notice that the first equation here, the v of t plus 1 given h of t plus 1, is found from our observation matrix. The next equation, p of h of t plus 1 given h of t, is found from our transition matrix. And as we saw before, p of h of t given v of t to t, all the past visible observations, the visible states, is given by the filtering solution. So again, it's easy for us to do these prediction problems given that we've solved the filtering problem. Let's lastly look at decoding. And in decoding, we're trying to find the path, the optimal path that has been taken through this hidden Markov model. And we can use the results we've gotten from filtering and smoothing in order to get these answers. And notice that all three of them, filtering, smoothing, and prediction, give us likelihoods at a specific state, whereas this particular problem is looking for a path. We could use the maximum a posteriori solution to find the most likely point at each one of those states. So the question is, why wouldn't you use filtering and smoothing to answer this path question? And the answer to that is that this map trajectory is not necessarily the most likely trajectory in the HMM. It's a little counterintuitive, but in fact, it's true that you can find the most likely state at any given point, but it may not be, when we look at the total trajectory, the most likely state that would have been taken by the hidden Markov model in order to get to where we are now. So that's an important point, and that's why we need this additional algorithm in order to find the most likely path through the hidden Markov model. And the algorithm that we use is one that's known as the Viterbi algorithm, named after its inventor. And we'll see how it works. So here's the general idea of the Viterbi algorithm. We have the joint probability, the most likely path that ends at state S and at time k. And we'll give that the notation delta k of S. So this is the most likely path then that we would find going up to some state S at time k. And the Viterbi algorithm is really like a lot of other answers. For those that you know dynamic programming, it's very much like the logic that we use there. We say, okay, we want to know what the best path is in this case up until some particular state, some particular time. So we're going to find the best path up until the previous time and use that recursively to help us answer the question. And we can define this joint probability of the most likely path using the maximum, so it's the most likely, okay? So we're going to use the maximum over all paths from the beginning up until the previous state, k minus 1, or the previous time, k minus 1. We're going to go all the way up until k minus 1 and ask, okay, consider all the paths that we could have gone on up until then. As I say, it's very much like dynamic programming. We're basically going to go one step back and say, gosh, we don't know what the most likely path is to the current state, but suppose we knew what it was up until the previous state. And that's all we're doing here. And we're setting that into this notation of delta k of S. And that's just this probability of when we look at the paths from 1 to k, the hidden state paths from 1 to k, what can they possibly be? And we're also, of course, considering the visible states that we've seen, and we've observed the visible states from 1 to k. So we want to take those visible states into account as well. So we're going to do what we've done over and over so far in these lectures. We're going to write this recursively. So we can write the equation for delta k. We can write it recursively, and we'll write it as delta k plus 1 of S now is going to be the maximum over all values of these delta k's, now given over looking at all the possible end states that they could have. Okay, so when we look, we're at delta k plus 1, and we're looking 1 previously at delta k, and we're saying, where could it have ended up? The maximum over all those values that it could have ended up in. And that's what the maximization is over. It's over all those Q's. And notice that then we're using this combination. We're using the combination of the transition matrix, which is the A matrix, and that's telling us the likelihood of going from Q to the current state S, the one that we're asking about. So if you look on the left-hand side of the equation, we're asking about S. We're saying, what's the most likely path that ends in S? Well, this is saying, look at all the most likely paths that could have ended in Q, and then we're going to look at the transition probability from that Q to the current one, S. And in the same way, we're also using the observation probabilities, which is the probability of observing the value of the current visible variable, v of k plus 1, given the hidden state S. And we iterate through this process to find the most likely path that ends at state S. So here's the Viterbi algorithm then written out. We initialize, and the way we initialize is we take these deltas and we set them. We look at the probability of being in a particular state where this is 1 through h, all the possible hidden states. We're looking at that probability and we're multiplying it times this observation probability of being in that state and observing the actual value that we observed, which is the value of the visible variable at time period 1. So we also set the previous state for time 1 to null, since we have no previous state. Now, we repeat for all the time from 1 up to t minus 1, up till the present minus 1, where S is, again, all the states in the hidden units and the hidden nodes in the graph. And what we're doing is we're setting our delta, this marker for the path. We're setting it for k plus 1, and notice we're starting at 1, so now that means delta will start at 2 and go all the way up to t. And we're looking then at over all the paths coming up to, let's say, 2. We're looking at all the ways that we can arrive at the different hidden states for time period 2. And again, we're using the transition matrix and we're using the observation matrix and the probabilities within those. We set the previous state at for S to the argmax, to the one that's the best of all of these. That's what we're going to set it to, and that's how we're going to start building up our path. This previous k plus 1 is a way for us to build up the path. And then we're going to select the most likely terminal state as the argmax of all these deltas. That'll be the terminal state over all S's. And again, S are these states within the hidden units, the states that the hidden units can take on. We'll then backtrack to find the most likely path, and we'll do that for starting at t minus 1 and go all the way back to the starting time period. We'll set k star equal to the previous period. So again, we'll start at the end and work our way back using this previous marker to find the optimal previous point, and that'll help us to find the optimal path then. So the joint probability of the most likely path in the observations is then going to be given by that delta at our current time at the optimal state at the current time. And for our example of Sally, here's the solution. And notice that we start out, as not surprisingly, with that 0.600 that we saw again. That's the probability that the alarm in room 1 is going to go off, given that the burglar is in room 1, and then zeros for the others because we know that they're in room 1. And we set this previous 1 to null. And you can see we gradually build up these values using that iterative procedure that we just described, that recursive procedure we just described. And the answer in this particular case is the most likely path is a probability of 0.04. Not very high, but remember that there are 27 of these. So this is the highest one. And then the most likely path, the end state, as we saw, is 3. That's what we saw from the filtering exercise. And the most likely path then is starting at 1, going to room 3, and going to room and being in room 3 at hour 3. So there's the most likely path for this particular example. So this then concludes our discussion of inference methods for hidden Markov models. So this then is a good way for you to understand how these HMM models can be used.